Good evening, sir. Saravanan, sir, shall we start the session, please?
Okay, thank you, sir. Good evening to one and all. So successfully we conducted session 1 and 2 yesterday. Now we are with the support of Atal sponsored FDP as well as your supports. We are continuing, we are entering into day 2. Now we will invite our session speaker P. Devikaran sir from Mobility. Sir is working as an assistant manager and sir completed PhD from National Institute of Technology, Karnataka, and MTech from Power Electronics and Rails from KL University, and sir completed BTech Electrical and Electronics Engineering from JNTU, Hyderabad. Presently, sir is working in mobility company as well as sir worked as a Axiom Energy Conservation Limited as a team leader and R&D departments in this product developments from February 23 to present. Sir is working now. As well as sir has worked as a junior research fellow in National Institute of Technology, Karnataka during the period of December 2017 to August 2019. Under this period, sir worked under a project titled the development of cost-effective magneto, that is rheological, that is MR fluid damper in two-wheelers and four-wheelers automobile to improve ride comfort and stability. Now I will hand over the sessions to Dr. Devikaran sir. Please.
Thank you, Saravanan sir. I hope I am audible to everyone.
Yes, it's audible only, sir.
Yeah, thank you very much.
Yes, sir.
Welcome to you all for this session, and I am very much thankful to Atal as well as Holy Mary Institute of Science and Technology. So, without any delay, shall I start the session? So, let me present my screen then.
Sir, Manoranjam sir, what's your issue, please?
No, he is specifying that he is audible. Yeah, sure, sir. Thank you.
Share your PPT. Okay.
Yes. So I hope you can see my screen. Can
Yes.
anyone
Yes, sir.
confirm by voice? Yes. Thank you one and all for this opportunity. I have chosen this topic for design and emulation of electrical vehicles for sustainable development. I'll give you a brief introduction in this aspect in terms of electrical as well as mechanical concepts. So when you go into electric vehicles, let us say for a four-wheeler, we have this basic layout of a four-wheeler. Okay. So in a four-wheeler, the basic fundamental parts which we see are traction motor, basically, which actuates the actual motor, and actual ride for the vehicle. And this ride is powered by the traction battery pack. Okay. And to control this entire thing, you have certain elements which needs to be controlled. For example, the power electronic controllers, which is in terms in industrial language, you call it as a VCU, vehicle control unit. Okay. So that, as well as for the battery to charge, discharge, and other aspects and functionalities, which I will be telling you inside, those will be controlled by the BMS. Okay. And for the lighting systems, which we have here, the lighting, I'll take the highlighter. Okay. Sorry. Or a laser pointer. Yeah. So for controlling these lighting systems or the thermal systems, or you have some clusters and all, present inside the deck board. Let us say your entertainment system or your mobile charging sockets, whatever they are. They need a lower level of power, which can be fed from the DC-DC converter there. This is a buck converter, basically. Okay, and we need a cooling system for cooling the motor or the radiator or whatever the system inside it. And you also, some things are which are not specified in this image, which are like a preheating system, which I don't think in India you need a preheating system, but if you're considering overseas, there may be snowfall, there may be temperatures which are into -°C. In that aspect, you will be requiring thermal heating system to preheat the vehicle. It is required for electric vehicles also. You might be thinking that it might not be required because electrical batteries, whatever they are, which may be lithium-ion batteries or whatever it may be, they perform better when they are in an optimal temperature, wherein which it might be between 30 to 50 or somewhere around °C, or which are not in -°C. It reduces its performance and it cannot, provide enough currents in that aspect. So in that aspect, you need temperature heating system also. But basically in India, you can say you need a cooling system. Okay. So again, charging, external charging and onboard chargers are required so that it automatically charges. Onboard chargers are required because you put the charger itself inside and only the AC plug is required to charge it. Of course, the socket may differ based on the EV guidelines, but basically you need a charger here, okay, and an auxiliary battery just for the startup and heating and cooling of these thermal systems. Okay, so I hope this is clear. So let us go into some mechanical aspects. So here the mechanical aspects are basically the traction as well as its suspension in a broader perspective, I am telling you. And I am focusing on the suspension system. Okay. Basically, suspension system, most of you might not be knowing because you are from electrical background. Suspension system basically has a spring, a damper tied up to a tire or the vehicle tire, so that this suspension system, whenever a jerk in the road or a ditch or a pothole or a bump is arriving at the base level of the road, this spring takes up the energy wherein which the bump is exerting, and it will transfer the energy to the hydraulic damper. Okay. So once that energy is transferred to the hydraulic damper, this damper has a hydraulic piston inside, wherein which this damper will radiate that particular energy in terms of heat. Okay, so this is the mechanism wherein which you will automatically subside that energy which is taken for the spring. Imagine a case where this hydraulic damper is not present and only a spring is present. So until the energy reduces, maybe 1,000 iterations or 10,000 iterations, it will keep on oscillating. The vehicle body will keep on oscillating and it will be like a roller coaster ride. Okay. So in order to reduce that energy instantaneously or within 1 or 2 cycles, this hydraulic damper is present. There are few calculations in order to how these dampers are being calculated. Okay. How these dampers are designed based on that, you have certain calculations. Okay. I will go through it in a brief. Okay. So I hope this is clear. So basically, in a vehicular suspension system, you have inertial masses, the mass of your chassis, vehicle chassis, and the restoring elements, which are the springs, which I have seen, suspension springs, which are shown here, and the dampers. The dampers are the dissipating elements. So this is the suspension system overall in brief. Okay. So if you consider the typical types of suspension which you are using in your car or in your bike or whatever it may be, that is a passive suspension. Okay, you have a damper which is fixed. In this damper, you have a hydraulic coil, and this hydraulic coil will be exerting the force for energy release. Okay, so in terms of friction or different mechanisms, you can expect actually. Okay, so in this aspect, your spring takes up the energy from the tire and dissipate it through the damper in terms of heat energy. This is the passive suspension which you kindly mute it. I am sorry, whoever it is.
Sorry, sir. 1 minute. Checking that.
Yeah, yeah, please.
Now, okay, sir.
Yes, thank you very much. Yeah. So basically, this is the format in which the energy taken from the tire will be transferred to the spring, and the spring will in turn transfer it through the damper. Same thing happens here too. In the active suspension system, there are three types of suspension basically: passive, active, and semi-active. What you find in India is mostly passive suspension. Active suspension is for certain vehicles wherein which you need very deep type of suspension, wherein which you need ultra high comfort for the vehicle. You can observe these in F1 cars or some race cars kind of approach. Okay, in that system. And there is something called semi-active suspension system, wherein which this damping, however it damps with hydraulic or whatever it may be, this particular dampening mechanism, what we'll use, it will vary the damping coefficient, which is said to be the, let us say you are adjusting it, like adjusting the rheostat of an knob. Okay, it may be electrical, it may be mechanical, it may be with different mechanisms. You can vary that particular damping, and based on that, it reacts based on the road actually. That is the semi-active suspension. So my research in my PhD was mostly on semi-active suspension, and I have published 2 patents on this. I have designed one new damper, as well as I have worked on some hydraulic fluid, which is MR fluid, and I have published a few papers and also appeared for another patent actually, how to create that fluid. So coming back to this part, as I have shown you, this vehicular body, this is the unsprung mass. Unsprung mass is nothing much. It is actually your tire mass along with the extra mass whichever is present along with the tire. Let us say in the previous figure you can see this particular arrangement for the tire which you are placing. This also has a few, I mean, it's a bulky mass which you can consider it as a another mass below the spring. It is simply below the spring and above the spring. Okay, so above the spring is the vehicular body, and below the spring, this is the tire as well as the unsprung mass suspension. Okay, so based on these 2 suspensions, we can find out the movement of the particular vehicular body. Let us say MS is the vehicular body, actual body wherein which you are seated. Okay, and this MUS is the tire unsprung mass, which you cannot change or something like that. So considering this as well as this, you formulate few equations, and this is these are the quadratic equations wherein which the system is expressed in terms of acceleration as well as velocity and displacement everywhere. Okay, so these are a few basic equations, and this system is called a quarter car system. Let me tell you, a quarter car system is considering one tire of the entire car. Okay, so quarter part of the car. So So when it comes to magnetorheological dampers, I'll give you a brief explanation on this. So magnetorheological dampers are basically hydraulic dampers, wherein which here the fluid is called the magnetorheological fluid, other than the normal hydraulic fluid like four coil. You can just get it in your mechanic shops. In that four coil, we will add some impurities like iron filings, etc., iron powder, along with some additives to make sure that it creates some viscosity. So this particular arrangement, inside the damper, you will be putting a solenoid. Okay, so when the solenoid gets excited, the fluid between these two poles in the solenoid, near the solenoid, gets also excited, making this viscous iron filings to create a viscosity higher than the actual viscosity of the fluid, thereby creating a higher friction there based on the viscosity, thereby changing the characteristics of the damper. So in this aspect, you can design two types of dampers. This is axial design, and this is a radial design. Okay. So this is about, this is a brief idea about suspension system in magnetics. Using magnetics, using the passive suspension or the active suspension. So if you have any doubts, you can raise it now itself.
Participants, if you have any doubt now, please.
Because once we get back to the electrical parameters, you might not get back to this. I mean, it is hard to remember going back again. That is why I'm asking you topic by topic.
Okay, sir. You
Okay,
continue.
Yeah, shall we continue? Yeah.
Anybody?
Okay, sir. Okay.
Yeah. Okay. So another major part in this vehicular emulation or the design of the vehicles is the battery management system, BMS, which we call it in brief. Okay. So how do you define a BMS, and what does the BMS do? So the basic battery management system is basically a technology wherein which you are observing the entire battery pack, which is present in terms of cells. Okay, there are different cells connected in rows or columns, in series, in parallel, multiple ways, and to observe its targeted voltages, currents, how far the lining is present, how far your connections are present, how far the voltages are reflecting, how far it is discharging, how far it is charging. Every scenario, everything which the battery is being operated is being monitored by the battery management system and is also being controlled by the battery management system. This is what its functionality, and this is what it does. Okay. So if you consider major functionalities, these are not just the functionalities, you have many functionalities, but I am specifying you some major functionalities here. Okay. The major functionalities are monitoring the battery, the condition of the battery. Every cell is being monitored by the BMS. Okay. And providing the battery protection. Okay. It protects the battery from external overcharging, undercharging, or high charging, or let us say internal discharge, or every aspect. It protects the battery of each cell. Estimating the battery's operational state. So basically this battery operational state, you can say it as SOC and SOH, the state of charge or state of health of the battery. That means at every instant of time, like for certain cycles of the battery gets worn out internally due to the chemical reactions internally. Basically it is chemical engineering. So in order to estimate it, the battery actually uses SOC and SOH, state of charge, the amount of charge it is taking, and state of health, the maximum amount of health it can contribute. I mean, let us say after 1 year of usage, the health of the battery is not same as the health when I bought it new. So this has to be estimated. So that operations also will be performed by the BMS.
இந்த 4 லிட்டர் மாடல் இது
Continuously optimizing battery performance. Okay, so in optimizing the battery performance, again, you are using these two SOC and SOH internally. And one more thing is you have battery cells which have different chemistry. Even if you are taking the same cell, let us say we are taking a Panasonic make, okay, cells which are 3.7 volts nominal voltage. Okay, even if you are fully charging them, one cell might be showing you 4.3 volts at full charge, and the other cell might show you 4.5 volts or 4.6 volts at full charge. So if you are using both the cells in series or parallel, okay, and you are drawing current from it, just understand that you are connecting it in parallel or series. One particular cell draws, discharges more than the other. So this internally creates a chaos and destruction of the batteries or cells will happen. This is being optimized internally. You can say it how, okay. And reporting operational status to external devices. This is very important, wherein which BMS, when you are put in a vehicle, it connects with the entire vehicle. Basically, it runs through CAN communication. I don't know how many of people know that, but basically it communicates the entire data with the vehicle. It communicates the data with the charging port also at the same time. So this is one particular functionality. It has many more functionalities like insulation improvement, insulation verification, its status checking, everything. But these are some prime functionalities which we are going to discuss in detail. Okay, so considering the battery monitoring, okay. So when it comes to the battery monitoring, if you can check this particular image here. So each cell has to be monitored internally, and in an overall view, the entire battery will be monitored. For example, if you are considering a lithium-ion battery, the lithium-ion battery will have a safe zone. SOA means safe zone of operation of area, or safe zone of operational area. So basically, when you are charging or discharging a particular cell, it has its safe zone. Like for discharging, for peak discharging, it shouldn't go more than 8 amperes. Here in this example, it may vary based on the battery. Okay, it should not go more than peak charging for 15 amperes. Okay, these are the limitations of the particular cell, and it has to obey these particular limitations. If you are not obeying these particular limitations, it is out of the picture. Okay, so again, for this is for peak charging and discharging. At peak charging and discharging mostly occurs when you are connecting it to almost dead battery, or maybe a 10% of charge is left out in the battery at that point. Okay, you cannot expect this peak charging or discharging to be performed at 90% or 95% of your SOC, or a state of charge. That means 90% of battery is already charged and you are expecting it to go into 15 amps. No, it won't support. And if it supports, the battery or the cell might get damaged. Okay, so this is one example which I am showing for battery monitoring. I hope it is clear. Okay, next, battery protection. The same way it protects the battery, as I gave you an example, the same way it protects the battery, and it has to only allow peak charging and discharging values for the particular limits. If the particular cell is already charged to the maximum level, it will discharge. It will stop the charging. Okay, it will charge to the maximum of 4 volts in this particular example. Normally it can go to 4.4 or something. But here in this particular example, it is a generic example. Okay. So for this continuous charging is generally observed between this particular, let us say some 3 amps, minus 3 amps to plus 3 amps. So discharge can be observed of continuous discharge to, for example, minus 3 amperes. 3 amperes, and charging also till 3 amperes. And from there, it is based on the state of charge and state of health of the actual battery. Okay. So another major thing in this aspect is the thermal management of the particular battery. Battery in the sense I am telling about all the cells, individual cell also. Okay. So what happens in actual scenario is each cell doesn't say that my temperature is like this. Okay. It may not. It may have or may not an internal temperature sensor. So temperature sensors are generally placed between the cells to observe the actual temperature in between the cells. And one temperature or one or more temperature sensors are present at the external to observe the external environment temperature. Okay. So the change between these two should not be within certain limits. You can see here the change between them should not be greater than 20 degrees centigrade. So in that format, you can actually check the thermal characteristics of the actual battery. So for example, if the thermal range of the battery is between minus 20 degrees centigrade to 60 degrees centigrade. Okay. So if it is going beyond the 60 degrees centigrade, it automatically trips off the charging or discharging. Okay. Same thing happens with different aspects. So thermal management is very important because once it goes beyond the thermal runoff, the entire battery will be blasted. So it takes very serious measures when it comes to the thermal protection. So we come to a point where it is very, very important, the estimation of the battery. Okay. So in order to estimate a battery, its life or its energy present inside it, the amount of energy it can capture it is based on two particular parameters. One is state of charge and the second one is state of health. And these two internally are also dependent on something called self-discharge. Okay. When left out alone, the battery, if it is left out alone, it will discharge itself at a certain rate. That particular rate is called self-discharge rate. Okay. If you are putting a car battery alone or the car to be switched off for months, automatically you will observe that the battery gets discharged completely and you have to externally charge the particular battery. This is what I'm telling about the auxiliary battery in your IC engine vehicles. It will be same as that for the actual traction battery also. So in that aspect, the particular BMS also estimates its self-discharge content. It also estimates its state of charge and its state of health. So let us say how this particular thing happens. Okay. So basically what state of charge says that is state of charge is the capacity remnant in the particular moment of the battery to that of the total capacity in the battery. Again, this total capacity of the battery varies with the health of the battery. So the health of the battery is internally a parameter for the state of charge estimation. Okay. So you're generally expecting a 0 to 100% of the state of the battery where you denominate it. But still, even if it is completely discharged to 0%, that doesn't mean that your battery is 0% discharge. That means no energy is left out in it. There will be some energy left out in it. And the barrier of 0 to 100%, which is put industrially, you will get at least 20% inside remain. But it is dangerous to operate it in that particular area. Okay, some 10 to 20% you will be having a spare energy inside it. So that again I'm telling you, so that if the battery completely drains out and you are charging the battery instantaneously, the battery will get overheated, and again it goes into a uncontrollable zone wherein which the battery will destroy itself. Okay, that is one specific aspect where you need to understand the importance of the SOC and SOH.
Next,
Hello.
சொல்லணும்னு நினைச்சேன் bro. சொல்ல ஆர்கே கிட்ட போனா நான் பண்ணலன்னு சொல்லிட்டு அதனால அப்படியே அதான் பிஸியா இருக்கேன், என்ன இது பண்ண முடியாது அப்படின்னு.
So in this particular image, you can clearly see that the amount of depth of discharge can be observed here. Okay, in the state of charge, you can see here. Okay, so state of charge, you are actually presently in most of the industrial aspects, you're using two main methodologies to estimate this particular thing. It is basically an algorithm. Okay, so one methodology is open circuit voltage methodology, wherein which at the open terminals of the battery you can check the open voltage, and based on the open voltage you can understand the state of charge of that particular vehicle. That particular battery. Okay. That is one thing. Second thing is Coulomb counting method. The amount of coulombs it is charging and the amount of coulombs it is discharging. This can be monitored, and based on that, you can estimate the state of charge. But these two methods are proven to be kind of primitive, and they won't give you the effective what you call the values. So there is always a very bad accuracy in that. So you can go with Kalman filter based technique, and there are many other techniques which are uprising in the present scenario. And in this aspect, we can aim for improving the accuracy of the algorithm. So when it comes to the Kalman filter, this Kalman filter actually is developed to estimate the unknown values with the available data in that particular period. This can be implemented in the vehicles because it is simple. It requires smaller computation power, and also it gives you a better accuracy and results compared to the previous primitive algorithms. Okay, so in order to implement this particular things, it is like a observer and updater kind of approach, wherein which you predict the step and you will update the values. You predict the step, predict the uncertainty, you will update the values, and again update the uncertainty, and you will update the space vector based on the SOC and SOH. These SOC and SOH can be, see, estimating these SOC and SOH, you will have a number of parameters which comes, like for example temperature, humidity, the voltage levels of the battery, the current levels of the battery, the type of battery which is being used, the chemical which is being used, many parameters you can see. And these can be truncated to certain levels, like modeling the battery in terms of RC based modeling, or 2RC based modeling, or something like that. So for that particular modeling, you can implement these particular steps, and you can estimate the actual parameters or the gain constant. And by estimating the gain constant, you are indirectly estimating you are improving the state of charge and obtaining the state of charge and state of health. So in that aspect, it will actually measure the previous uncertainty and give it as a input to the present state values and update it. So it keeps on updating based on the inputs observed. Okay. Similar to the state of charge, you have a state of health. Okay. State of charge, you can simply count it in certain aspect. I cannot say it is simple, but it is quite simple compared to the state of health. Okay. State of health is practically a serious estimation. And this particular estimation, let us say you're using your battery unevenly. Let us say if you are not using your battery in productive measures, not within the safe operating area or something like that, then your state of health will drain or drastically. So if you are maintaining that state, the particular battery within your respective limits, and using the battery within that particular permissible limits, you can obtain a larger health life. But how to estimate this particular state of health is a tricky thing. So again, it varies based on the humidity or the temperature, how much current you are drawing from the vehicle, how much voltage you are charging for the vehicle. The entire thing, again, it is interdependent on the BMS, proper BMS other operations. So in one aspect it is connected to the other. It actually, each aspect is important for the BMS to maintain and properly ascertain the actual battery health as well as the charge. Okay, so you can also evaluate this particular state of health by using Kalman filter techniques, and also different techniques. You can go with there are certain techniques called non-linear Kalman filter techniques, and also other techniques which can be implemented in this. Okay, so basically, why are we estimating this SOH in a what do you say, in a high performance manner or in an accurate manner? The reason is you have to evaluate its performance. If you have to predict its maintenance. Basically, if you are not able to predict its maintenance, now in some or the other way, the vehicle may get stuck in the middle of the road or the highway, where you may not have any charging point. This is one disaster situation which we need to avoid. So safety concerns. If you are not predicting properly the health of the battery might get damaged due to overcharging or over discharging automatically. This may create a hazardous situation for the passenger as well as the vehicle, as well as the battery. Okay. And second thing, if you are properly predicting everything, performance evaluation, as well as the maintenance, as well as the safety concerns, then you will be saving a lot of money in buying a new battery or something like that. You can extend your life and extend the life of the battery, and automatically the vehicle will also be used for a larger period of time. So this is one more aspect, the optimizing battery performance. So in order to optimize the battery performance, we need certain aspects, like you are always connecting the cells in series as well as parallel. Okay, so the generic approach which we use is we first connect certain batteries in series, and then you will connect those certain cells in series, and you will connect those cells, string of cells which are connected in series in parallel to get the effective currents. So basically, if while you are doing this particular thing, you need each cell to be of same voltage, or else if you are having a different voltages, if where you can see in this example, if all the cells are having same voltage, you will have 20 volts balanced voltages. Okay, but if you are having uneven voltage, okay, the unbalanced voltage will be around 18.8. This is just an example which I am showing you. Then again, don't think that this is the only problem with voltage. If you are using this particular voltage, pardon me, is it something which I have done? Yes, I think Mr. Rajendra has raised. Or is it Dr. Rajendra or Mr. Rajendra? Can yes, please. Do you have any?
No, sir, I am not Dr. Rajendra, sir. I am Rajendra.
Yeah, please carry on. I'm sorry. Yeah.
Sir, you are telling that balanced voltage may not available in all times, sir.
Yes.
How could we define that?
Yes. Sir, pardon me. How could we define that?
How could you find?
Yeah, basically every cell is being monitored here when it comes to BMS. Each and every cell has a terminal here. If you're sorry, if I'm sorry. So I think you can see my screen, right? Yes.
Okay.
So here from each cell, you will have a wire drawn. Okay. Each cell from here to here, you will have a wire drawn. So if between these two wires, you can measure the cell voltage. Okay.
Okay.
Okay. So with if that particular cell voltage is every second, let us say if you are setting certain time period for the BMS for certain milliseconds or for certain seconds, that BMS will always keep on checking this voltage. Okay, it is constantly checking these particular voltages. And if this particular voltage between these two terminals is less than a certain particular voltage, then it indicates that that particular cell is dying. So you need a charge. Okay. At the same time, if one particular cell is having higher voltages, very high voltages, let us say rather than 3.2 nominal voltage, it is having some 4.2 volts. Okay. And all the others are 3.2. Then it will actually have a switch connected across a resistor here, actually, which I have not shown here, pardon me. So this switch will be closed and it will discharge a certain amount of energy from this particular cell. And the resistor will transmit that particular energy in terms of heat. Okay. Until this particular voltage is equivalent to these particular voltages. This process is called cell balancing. Okay. Cell balancing is very prominent and it is very much required as a functionality of the BMS. You may not observe this in basic BMS, which we observe in low power applications like our normal, small BLDC controllers, which we use for quadcopters and all. But if you are aware, for larger systems like, for example, two-wheeler or three-wheeler or four-wheeler EV vehicles, then this particular balancing is predominant and you compulsorily need it. This particular balancing is called passive balancing. You have active balancing also, which is another phenomenon wherein which you can transfer the excess energy from one cell to the other cell. Of course, it has an more connectivity and more BMS functionalities, but I'm just telling you in prayer. So this is basically about the battery management systems on the whole. And yes, if you have any doubts, you can ask, please. Sure, anybody with doubts?
Sir, dear participants, anybody having the doubts?
No, sir. No,
Yes,
sir.
Sir Shiva, I think, sir, he has raised a doubt. Please.
So, Shiva will be raised and
Ammu Shiva.
please, Shiva,
Yeah, I'm sure. I think.
please
Yes.
raise your question, sir.
Hello, sir. Please respond. Okay, sir. Go.
Okay,
ahead,
sir. I'll start. I'll continue
please,
the
please.
session.
Go ahead.
And we can have another session. I mean, another question and answer session at the last 15 minutes if it is possible. Okay. So basically, this is about battery management systems, which is the major part of the vehicle in terms of my perspective. So I have gone through a few functionalities and the design aspects of this. So when you come towards the main thing, the traction motor or the EV motor, which you are specifying, okay. Basically, in previous situations or previous vehicles, you might have observed in the Tesla car also, the first design of the Tesla car came with induction motors or the induction generators, which you can observe based on the basic induction motors. Okay, and you all know the basic induction motor phenomenon, which is a rotating magnetic field. The field actually occurs in this format. Okay, this is the rotating magnetic field which you will observe in the induction motor or whatever the motor you can see with multi phases. Okay, this is how it works. Okay, the rotating magnetic field. So this is a primitive type of induction motor. Presently, the traction motors are completely updated to brushless DC motors. Okay, and you can observe clearly the difference between the two motors here. This is a brushed DC motor and this is a brushless DC motor. So the brushed DC motor has commutator and the winding present inside, and the brushless DC motor is actually the rotor or stator, whatever it may be. One is a permanent magnet, okay, and the other one is fed with the what do you say, a multi-pole rotor. Okay, the rotating mechanism is always a permanent magnet. The rotating mechanism may be the outer circumference or the inner circumference. Please don't get confused with the stator and rotor and the windings. Okay, the rotor can be on the external part. This can also be your rotor, and internal part can also be your rotor. The external part, which is a rotor, is called the outrunner, and the internal part, which is a rotor, is called the inrunner. So in your EVs, basically whatever the Ola or whatever it may be, the internal part is actually your stator. Okay, internal vehicle with windings. It is actually your rotor. Okay, sorry, your stator, and the external part which is there is the rotor. So based on the internal windings, the external rotor will also be rotating. Here, which I have shown, is a inrunner. So the rotor is present in the center with permanent magnets, and you are exciting the nearby pole, wherein which is the opposite pole is present. So automatically, this particular rotor gets excited and turn based on the pole which you are observing. Okay. So you can clearly see here, this is how you will be energizing the field in 120 degrees mode of operation in brushless DC motors. So this is the equivalent, the pink one or the, I don't know the color variation. The actual green one is the actual flux which is being processed, and based on that, your resultant vector is the brown or the pinkish one which you can observe. Okay, so this is how you are energizing a brushless DC motor in 120 degrees mode of operation. If you are exciting the particular motor in 180 degrees mode of operation, the particular vehicle, what you observe is actually having a torque of sinusoidal torque, which is not that much useful for traction. Of course, it is useful, but the torque will be varying, which creates a little difference. So most of them use 120 degrees mode of operation only. So here you can see this is the stator and the center part is the rotor, and you have certain Hall sensors present here, 1, 2, and 3. And based on the Hall sensor input, you are sending it to a decoding circuit or an intelligent circuit, wherein which it estimates the position of the poles of the rotor, so that based on this Hall sensors, automatically that particular nearby pole is being excited, and based on that your rotor is being rotated at full speed. In induction motor, as you know, it is an asynchronous motor. You will not be getting what do you call the maximum speed, that is the what do you say, magnetic locking. You cannot get the magnetic locking and you cannot go into synchronous speed. But in the brushless DC motor, the magnetic locking happens and at the full speed, and you can get synchronous speeds, which makes the particular motor special. So this is one more comparison of the vehicles motor, EV motor, with Hall sensors and without Hall sensors. Okay, this particular operation which is happening is called sensorless operation, which is without sensor. And here you have Hall sensors which can predict the actual pole presence wherever it is possible. Okay. So if you are doing FEMM analysis is finite element method magnetics. FEMM means finite element method magnetics, which means it actually analyzes the amount of what do you say, magnetic field which is being generated at position from position to position. So when you are checking the brushless DC motors FEMM analysis, this is basically a 9-pole BLDC motor here. So these are few poles, four poles, and this is 5 poles. So total 9 poles, and there are few poles here. I think it is 12 poles or something. So based on this magnetic field which is being generated, it produces the magnetic fields. These are the lines, magnetic lines of force, which are being generated. You can clearly see these magnetic lines of force. I will, if time permits, I will explain you how these emulations are performed actually. Okay. So this is one example how you see the internal magnetic field which is being generated in the motor. Okay. So I already spoke about this, the advantages of brushless DC motors. So they have better speed to torque characteristics. They have high dynamic response, higher efficiency. If you are considering induction motor, you get maximum efficiency of 70%. But if you are considering brushless DC motor, you can go up to 90, maybe 95 too. So it has very high efficiency. Longer operational life. Yes, it is a closed design basically. So you will get a longer operational life, and there will be no noise as there are no commutators. Okay. So when it comes to the control strategies, you can control the brushless DC motor in 2 ways. One is with sensored control, and the other one is unsensored control, sensorless operation. And sensored operation, you can use it by applying PWM control and also the hysteresis control. And when you consider the sensorless operation, you can use only one speed sensor, or you can directly control it by using the back EMF. Okay, so Here you can actually verify how the poles are being triggered here properly and how the flux waveform is being generated. Okay, you can verify it. You can observe this in TI website also. So basically, in this way, you are getting a back EMF, which is a trapezoidal back EMF, wherein which it helps us to actually estimate the EMF much effectively. Yes, I think somebody has a question.
Mukul Banaraju. Sir, please. Mukul Banerjee, sir. What's your issue, sir? Please. No, sir. Maybe
Okay, fine.
unknowingly, sir.
I'll continue. Yes. You can get this GIF images in TI website also. You need a little energy or to be invested basically. You can get it quite easily. 5 minutes of time or effort. So okay, so when you are simulating the stator currents of this particular brushless DC motor, I have done it using MATLAB Simulink. So you can observe the stator current like this, and the back EMF to be like this. And when it comes to torque speed characteristics, also you can get the same. Okay. So another predominant alternative for this brushless DC motor is the switched reluctance motor, which is coming into picture, and more research is being performed actually on the switched reluctance motor in recent days. IIT Madras also is performing certain research on this particular switched reluctance motor. This particular motor has an advantage. Basically, it doesn't use any permanent magnets. Basically. So the rotor part is actually an iron piece, basically an iron piece or a ferromagnetic piece, which has high magnetic permeability. So once this high magnetic permeability part is present in the rotor, based on the reluctance offered by the other by this particular ferromagnetic field, or uh, or you can just say the less reluctance offered by this particular ferromagnetic field compared to the flux passing through the air. Automatically, this makes this creates a force being generated on the rotor, and automatically, based on this principle, you can formulate this particular motor to be working conditions. And yes, this can be a better alternative, but only problem you will be facing is you won't observe the back EMF that easily. So sensorless operation becomes a very hectic thing basically. So there are certain limitations to this compared to brushless DC motors, which is very highly appreciable. You cannot also get uniform torque characteristics in here, whereas you can get the same uniform torque characteristics in brushless DC motors. So still research is going on the switched reluctance motors. Some people are still using it. They are manufacturing it, but provided with a lesser torque ranges, you will have a little bulkier wheel or little bulkier motor. So yes, you can simulate this, but as I have specified, I have tried with certain MATLAB models, and also I have tried brushless DC motors to be simulated using Simulink, as well as I have tried with the quadcopters or the motor which you get outside with the brushless DC motors. So I have tried sensorless operation on that also. So basically in the closed loop operation, you will get the speed torque characteristics, which I have shown earlier, the current and the voltage back EMF characteristics also. So this is one kind of experiment which I have done, which is basically a hub motor. It is a 250 watt hub motor, and using Arduino Mega, I have controlled it completely to use it as a basically a lift design basically here. And I have designed a control algorithm for this and made sure this control algorithm works properly on this. So this is one type of experimentation which I have done. And you can also perform a closed loop open loop or closed loop operation of the brushless DC motor control. You can see here, this is an open loop operation basically with the battery and a regulated power supply just to power up these what do you call optocouplers. Okay, and using the Arduino, I have controlled this brushless DC motor. Okay. So when I am doing this, I have generated the milliseconds pulses. I observed the pulses which are obtained in the by the Arduino with milliseconds of delay. So these are certain pulses. And I have shared this in the Atal website. You can verify these things. If you want, you can come back to me. Okay. And these are the current waveforms of the sensorless BLDC. You can observe these current waveforms here. And this particular triggering shows that my particular design is not that optimal. And these particular, you can see a sharp peak which is being raised, which should not be happening. And this might destroy the operation. We need to fine tune the particular control strategies. Yes, I think someone has.
Ma'am, Jyotiramai ma'am. Ma'am, Jyotiramai ma'am. What's your doubts, please?
So please continue, sir.
Yeah, okay, thank you.
Thank you.
So for the closed loop operation also, we had the similar kind of approach wherein which we have tracked the back EMF using one back EMF sensor, wherein which I tracked the back EMF and used it to give it as a feedback to the Arduino. Of course, my particular design, whatever I have designed, it is at quite low speeds, so I could afford to design in the Arduino in that particular aspect. But if you are using it at high speeds and higher accuracy, this kind of approach will not be that efficient. So at that aspect, you need to use what do you say? Field-oriented control or flux-oriented control, FOC. So these particular things you can do it in Texas Piccolo series, 2000 series. It comes with a supported design. So you can work on that if you are quite interested in this particular aspect. So these are the waveforms of sensorless operation wherein you can check the back EMF observed here. This is not a correct abrupt back EMF which is observed. You can see the pulses to be very sharp, and this will actually create a error actually. So the way the particular motor was rotating, but internally it is slowly getting destroyed. So this is one kind of approach which I have tried and I failed. So that's it for this particular session. If you want, I can show you some experimentations which I have done. And yeah, if you want, I can continue with the flux-based design which I have shown here. So FEMM analysis, I can show you how this FEMM analysis is being performed. Do you want it or not? Shall I stop the session here? It's about your intuition. What do you prefer?
1 minute. We will ask from the participant side.
So keep on continue, sir. 5 minutes is there, no?
Yeah. No, please don't listen for the sake of time. Please listen if you are interested itself.
No, they are
Yes, sir, we are
interested.
interested.
So basically you have something called, I think you can see my screen, right? you have something called FEMM 4.2. If you observe it clearly, I can show you. You can just Google it. You can just Google it, FEMM. Just Google FEMM and you will find this page. Okay. Finite element method magnetics homepage. It is a completely free design. You need not require anything else. It will help you design. It will help you design these particular what do you call it? Magnetic elements or the magnetic field, how it is being observed in different shapes. Okay. So how many of you already know this? Okay, you can raise your hand if you know this. Oh, okay, nice. Anybody else? Okay, so for their perspective, I'm just telling them. This is an example. Sorry. So you can see my screen. You can see my screen here. So I am taking it. Yeah. I hope you can see my screen, right? So here is a structure wherein which I have designed. Let us say I have designed a general rotor. Let us say a fan. Okay, a simple fan wherein which I am giving it. I am giving a DC supply to the particular fan. Okay, this will be my outer periphery, which is designed by 1020 Steel. Okay, you can actually check this particular materials here in the material library. Okay, so in this material library you can just go through this. You have different materials here: copper, solid, non-magnetic, solid magnetic materials, hard magnetic materials, different types of magnetic materials. You can go through this. Okay, and you have these points and dots which can be connected here. So points will give you points like this. Okay, and dots will line. You can connect a few lines and make a solenoid, and it depends on your requirement. So okay, and then in the problem you can generate the type of problem if the particular what do you say, if the particular design you are checking is a planar design or cylindrical design or whatever it may be. So you can check based on that. It's an axisymmetric or planar. Okay, I'm taking it as a planar, and I'm considering the length is to be milliliters or millimeters or centimeters or meters, and depending on the requirement. Okay, the size of the particular solenoid or the size of the magnetic item which you want to design. Okay, and you can leave all these as normal, basically the solver and the AC solver, whatever it may be. Based on the frequency you set here, you'll get the frequency there. So if you want to run that particular mechanism with AC supply which you have, you can set the AC supply to be 50 Hertz or 60 Hertz, whatever you require. So in that perspective, I have generated one iron core here, and similar iron core I have made poles here. If you can see this, these are the poles with 4 poles here. Okay, and these 4 poles are wound by a 24 AWG wire with 100 turns. So if I am giving plus here and minus here, that means minus 100 turns and plus 100 turns. Plus 100 turns means it is coming towards you, and minus 100 turns is it is going towards the simulation. Okay, so in that particular aspect, if you are giving 100 means it is 100 turns you are giving. Okay, and similarly in this material properties only, you can go to the circuits and you can design positive, define positive and negative. And if you are checking for positive, you can just check for positive and you can set the current how much current you are giving it through that particular copper wire or copper or aluminum wire, whatever wire you specify there. Okay, is it in series or in parallel? If you select parallel, all the wires will be in parallel, not in series. Okay. So this is how you actually design before you simulate actually. So after simulating, I have created a boundary here that I want my simulation within this particular area. Okay, and I have given a gap here, and in this gap I have poured some fluid, which is a magnetorheological fluid. Rather than that, you can use it basically airflow only, or if you want, you can use some magnetic flow or some anything, any other material which you want to simulate. Okay, so after simulating, you can just go to here and create mesh. Automatically, it creates a mesh with multiple nodes. So these meshes will make sure that your entire drawing or your entire system which you designed is being split into certain triangles. Okay, and it estimates the magnetic field. Pardon me. And it estimates the magnetic field within these particular triangles based on the method of successive approximation or Runge-Kutta method, whatever the method you have selected before. Okay, after that, you can just go and analyze, and it starts analyzing. Okay. So,
Sir, Ramgopal sir, please sir. Continue.
so once it is analyzing, what is it is analyzed, you can just go and view the results. It will show you an image in this format. Okay. So once if you want to see the direction of the magnetic field, you can just plot here B or H, whatever it may be. I'm checking as B. So see, the direction of the magnetic field is also observed. And I'll check it out. Second. Actually, enlarge it and I'll show it to you. So you can see here, this is how the magnetic field is going through. Okay. And again, if you want it to be displayed in a very good diagrammatic representation, show legend, show density plot. That's called density plot. So it will show you in colorful notation. Okay, how much Tesla of field is being generated and how much field is passing through at different points of contact. Okay, so if you want to check again, I can.
Sir, Devikiran sir.
Sir? Am I audible, sir? Hello?
1 minute, sir. Checking.
Yes, sir. Audible.
Audible.
Yes.
All.
Yeah, I don't know why the disturbance. Okay, fine. So you can clearly see the density marked based on.
Devikiran sir.
Yes.
If you don't mind, due to time constraints, we have to start by next session by 7:30, sir.
Okay, fine. This is enough. I think I'm just concluding it
Yes,
basically.
yes. Actually, your session will be going very nicely, sir. Okay.
Yeah,
It
it's
will
okay.
be very interesting, actually.
Yeah,
We are requesting due to time constraints, sir. Okay.
So fine. I'll close it within 2 or 3 sessions, 2 or 3 minutes. Yeah.
Okay.
So
Please.
these points, if you check, considering this point itself, you can check it here. Okay, you can get all the details of that particular point here. If you want, you can check it here. the total amount of flux as well as the intensity. Okay. And if you want to have a graph, okay, you can check from here. You can check point to point and point, 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 point. Okay. You can check it. So everything will be displayed here. Okay. So this is how you analyze your magnetics in a particular magnetic material or the item. You can use different aspects, solenoids or something, and beware, this is actually a 2D analysis only. If you want to go for a 3D analysis, you have to go with ANSYS or any other FEMM device, which can give you a 3D perspective. So with this, I'll end up my session. And if you have any doubts, please go ahead.
From participant side, if you have any questionnaire, please, this is the time for you. Sure. Sir, please. Subhaganesen, sir.
Oh,
Please
thank
take
you,
the
sir.
session.
Thank you, Saran. So thank you very much. Good evening, everyone. It's indeed an honor and a privilege to deliver the vote of thanks at the conclusion
Yeah,
of sustainable development. First, hello.
Yes,
Sir,
please
it is,
carry on.
sir, audible only. Please carry on.
Yes.
Yeah. Okay. Thank you. First and foremost, I would like to thank to our esteemed speaker, P. Devikiran, for sharing their invaluable insights and expertise. Your thought-provoking discussion, understanding of electrical vehicle, but also highlighting the vital role of the sustainable development. I extend my gratitude to the faculty members, participants, and the staff who have joined for us, various institutions. Your active engagement throughout this program have made it an interactive and fruitful experience for everyone. Thank you all once again for your participations and support. Wishing you success in your endeavors. Have a wonderful day. Thank you.
Okay. So participants, now just leave the session, and after the 5 minutes, you just join in the session number 4 links. Thank you. Thank you for your support. The same we are expecting.
Okay, sir.
Okay, sir. Thank you. Thank you very much.
Thank you, sir.
Thank you. Thank you, sir. Devikiran, sir.
Thank you, sir.
Yes,
Thank you.
thank you all for your
Nice.